And today we're going to just look at a couple of notebooks, Jupyter notebooks on the Colab system that implement a couple of graph neural networks that process core data set. So yeah, to access them, you just open Colab, go to the GitHub tab, input MLSS-Scultech, and choose the MLSS tutorials week 2. And then you're going to see the list of notebooks. And we're going to start from this one, Core GCN. GCN stands for Graph Convolutional Network. This is like one of the most popular architectures. Original one was implemented by KIPF in 2016. And it's pretty simple. If you remember the lecture by Michael Bronstein last week, he described that the architecture of this neural network is fairly simple. Because what it does is just each layer of this neural network creates some hidden layers of this neural network. They just essentially just make a multiplication of the Laplacian of the graph, which is specially prepared adjacency matrix multiplied by features of in the nodes of the graph and multiplied by weights, essentially parameterizing this layer. Then you can use some nonlinearities and do so as much as you like, as many layers as you need. And the properties of this neural network, yeah, first I want to talk a little bit about data set that we're going to look at. This is a core data set, fairly simple. Think of it as maybe a MNIST, but for graphs. Quite popular. And it implements, it's a small subset of a citation graph where nodes correspond to papers, science papers. Labels of this graph, each node has a feature vector, which actually just one-hot encoded some of the keywords, most frequent words in those science papers. And those one-hot encodings are going to be used as features, and the labels for them are category of the paper in which subfield they are actually published. And the edges are citations and references. So you can see, looks a little bit like this. This is probably just a forced layout of this graph. And it has 2,700 nodes and 5,500 edges. Fairly small, relatively to things that are you can encounter in industry, like a graph, like for social network or a recommendation system, like at Netflix or something, is going to be millions and billions, and connections are going to be also a large number of them. So let's proceed. Some of the cells going to take some time to compute, so just start running them. There's not going to be any task. Well, if you want to code something by hand, I recommend just compute some of the metrics, start training the network. We're going to go through it in detail right now. So this simple neural network, what it does is just, as I mentioned, multiplies the Laplacian of the graph by feature matrix and weights. And after several layers of this neural network, we're going to compute softmax and going to get the, you need to make it larger? Okay. Is it better? Okay. Yeah, if at any point you have questions, just like raise your hand and I would be glad to answer. So yeah, the computational aspects of neural networks that work on graphs, there's two major setups how they can work. One is where you have a large graph and it's going to be the whole data set. And another setup is where you have multiple samples and each sample is actually a graph with some properties. For example, if you have, let's say, some other things like images or point clouds or some geometric representation in each sample, like a point cloud of a shape, registered of a certain shape, and you can convert it into a graph. So each sample is going to be just a separate graph with separate number of nodes and edges. But usually, if you have each sample has the same number of nodes, it makes things much easier because you can represent them just as matrices or something like that. So the implementation, unfortunately, in TensorFlow, not my favorite framework. If you're going to take away anything from this tutorial, is that if you want to do something with neural networks on graphs, better to use PyTorch and specifically PyTorch Geometric. This is a framework developed by a PhD student in Germany, and it's really good. It's much better than the things I'm going to show you right now. Because it has a really neat framework of how you can think about neural networks on graphs. Instead of like implementing a lot of boilerplate stuff that is going to be the same across all of the different papers, different neural networks, you can think of any neural network that works on graphs has like three properties. One is like it has an element that changes the information in nodes. So think of it as like a forward layer, but for each node, which knows its information about surrounding nodes. You have a question? Okay. Can we zoom more? Yeah. So this is a specific framework. You can implement almost any graph neural network by just writing three different methods that take into account separate parts of the processing that takes place in neural network. There's a forward method that changes properties, computes hidden layers based on the properties of the node. Then there's a messaging part, which takes the information computed on the forward pass and spreads it around the graph effectively. And then there's a third method that is not listed here, aggregation, which takes this messages passed along the graph and the properties of the node and aggregates them together into activation on the next layer of the neural network. So this framework is much better because you're just writing three different methods, selecting effectively, and you're gonna have almost all of the variability of graph neural networks. For example, this PhD student, I think like from first year PhD student, re-implemented all of these papers, all of this, for the last these papers, different kinds of graph neural networks papers came out in last, I think 3 or 4 years. And yeah, because this abstraction is so much better, it's so easy to implement like all of these papers because you don't need to do a lot of boilerplate. Speaking of boilerplate, so there's a lot of tricky parts when you're implementing graph neural networks in code. There are several problems that everybody encounters. How to represent adjacency matrix and Laplacian, because for example, if you have, let's say, 2,700 nodes, your adjacency matrix, if it would be dense, it would take like millions. It's going to be a huge matrix, right? A huge waste of memory. So the problem is how you, is your deep learning framework can work with sparse data? This is going to be the key question. But now, mostly PyTorch and TensorFlow already have the capabilities of working with sparse tensors. But it wasn't always the case. It was quite tricky, maybe like 2-3 years ago, to do something like that, to have like capability of auto-differentiating like computational graph without sparse operations. So yeah, let's see some boilerplate. So this is just class that encapsulates the definition of the neural network. So, for example, we're just creating a lot of, what do you call them? Placeholders, constants, defined weights. This is going to be the simplest two-layer neural network, as simple as it can be almost, with some dropout, by the way. Then, when you have the sparse tensors in your deep learning framework, it's also important that you have multiple different operations which can take sparse and dense tensors and multiply them, sustaining the ability to auto-differentiate. It's really important. Because sometimes if you have non-trivial things going on in your neural network, it can be quite problematic to make it work, because not all operations can be implemented sometimes. Yes. So we have this large graph. We have 3 sets of indices for train set. So subset of nodes of this graph are going to be our training samples. Some nodes are going to be tests and validation accordingly. We also going to be using some L2 regularization, but yeah, over here it's quite simple, easy to understand. Yeah, we're just defining optimizers, creating auxiliary variables to observe the behavior during training time. Yeah, and some metrics just to. It's a good idea to have like something like this. Compute metric of your gradient, so you can see what's actually going on during training time, because these non-typical neural networks, their gradients might just explode or vanish, and you're wasting a lot of time effectively if you don't see how the process occurs. Yeah, let's start running this. Ooh, spicy problems. You know, if we were not going to be able to resolve this right now, we can, we're going to have some technical assistance right now. Nope. Forget about it. Anyway, so maybe you're going to be able to fix it yourselves, because it's quite tricky to get this data on the collab. That's really unfortunate. So yeah, we have some scripts to pre-process this data. Yeah, as I mentioned before, like all the things that's happening actually in pre-processing stage is we taking this adjacency matrix, converting it into a sparse format that the framework can use, adding the loops for the nodes, self-connections. Each node gonna have like a connection to itself, so it can propagate features forward, activations. What was it? Yeah, self-connections. Subtracting the degrees of the nodes, and that's going to be the Laplacian that you're going to be using. multiplying it by feature matrix, weights. Yeah, and it's gonna go forward like that. Then we also have a train loop down there, really clunky. Just a lot of boilerplate stuff. It's not really interesting, actually. But the main ideas behind it is just the things you need to know about the graph neural networks in this context is when you have like a training procedure on one large graph, you're not going to be batching anything in a trivial way. Well, if you have a large graph, you're probably going to need some batching. But what it does is just takes the same sample, takes the same graph, and it iterates it multiple times until it converges. But we're just doing this optimization on subset, on training subset of nodes, and we're going to be testing on the validation. Yeah. So the kinds of problems that you can solve like that, somewhat limited, because not always, well, if you have a graph and you need to compute from some properties of the graph, other properties like labels or regression, you can do that. But there's other kinds of problems where you have like multiple samples. Each sample is a graph. It might get non-trivial because sometimes the number of samples, number of nodes in each sample might be different. In that situation, it's usually you can either try to equal them out just by dropping some nodes if it's non-essential in your context. Or you can use some different architectures of neural networks that can operate on variable number of nodes. So technically nothing constrains the neural network working on graphs with different number of nodes, but sometimes the ways that the neural network learns, the optimized model, can be specific to this scale of graph. So that might be the problem sometimes. It might not generalize well. Any questions at this point? Because we have some problems. Let's talk a little bit. Forget about it. So yeah, if you want to look at the evolution of the graph neural networks, just go to this repository, PyTorch Geometric, and you're probably going to find like 90% of well-known neural networks that were implemented at the conferences and published. Usually you can find re-implementation there. And the changes that happened in the architectures, not really drastic. For example, if you remember the tutorial, the lecture by Michael Bronstein, he showed like a sequence of slides where only the forward operation changed, and they provided a lot of rationalizations like from spectral theory why those different kinds of forward propagation mechanisms are more valuable. And usually the reason is that it can aggregate information from farther away from different nodes that are far away, effectively. And this is almost the only thing that is different among a lot of those graph neural networks. And the second class of graph neural networks that can operate on variable number of nodes, they usually have some interesting things like pooling operations that change the adjacency matrix along the computation of neural network. So this is kind of hard and not always work with graphs, because when you start changing adjacency matrix of your graph, it becomes non-trivial. Like, if you want a neural network that can change the adjacency matrix, it needs to have some mechanism of knowing how to aggregate them, how to drop some of the nodes. And a lot of innovation happened in that sphere. Because when you change the adjacency matrix along the way, it's almost too much to ask from neural network because it sometimes cannot learn effectively, becomes really unstable. I mean, like, when the guy's going to be finished, we're going to be all the time. So, I don't know. We have a second notebook that may be working properly. If you go back to the collab page and open the MLSS, it's going to be named core_GAT, G-A-T. And this is a variation on the GCN, which takes quite popular element in deep learning right now, transformers and multi-head attention layers, and applies them to the graph neural network. Because the thing is that almost all of the, forget about it. It doesn't matter if it works or not. We abandoned that idea. Okay. So yeah, the graph attention neural network. So in general, your equation for each node looks like this, right? You have activations on the next layer, gonna be a sum of the surrounding activations of the nodes multiplied by some weights. In GCN, weights are the same for all of the possible edges. But you can also use something that uses effectively labels edges and applies different weights to edges with different properties. That's another flavor of graph neural networks. But in this architecture, the difference is not with weights. The difference is how we compute the normalization factor. And in attention, this graph attention network, this normalization constant is an attention mask. How many of you know what is the attention layers or like multi-head attention? Some of you, great. So yeah, effectively, we compute first generation of hidden activations of the nodes. Then we pull them through we concatenate them together across two nodes, connected nodes, concatenate them, multiply them by weights that are computing attention mask, and then this attention mask, we were putting it through the softmax layer, and then multiplying those hidden layer activations of the nodes, multiplying them by attention mask, and aggregating them. And it enables this neural network to know which nodes, which features, which activations from which nodes are going to be more relevant to the computation of the next activation on the next layer. You know, we're going to fix them, and maybe after hours, if you want to poke at them, or on Wednesday, maybe you can have a refresher or something. Just go through them with working, yeah. So when they're going to be working. So yeah, the GAT neural network, it has a lot of the same boilerplate that I was been talking about. But here we have just defining the attention layer, which is also going to be a sparse matrix because we need to multiply it, multiply the Laplacian with attention mask. Yeah, effectively just the complicated part here is that you need, if you're implementing that by yourself without using any deep learning frameworks for graphs, the tricky part is going to be that you're going to have hidden layer, activations of the next layer of the neural network, and then you need to concatenate together activations across edges. Only the nodes that are going to be connected by edges, you need to take activations from them, concatenate them, and multiply by attention weights, so you can compute this attention mask. And this is tricky because your deep learning framework gotta have the gather operations, which can take those indices from adjacency matrix, resolve them, put them together. Hmm? Oh, you have a question? Yeah. Yes. It's going to be renormalized because each computation is going to be happening for each node, and when you're computing this for each node, we're going to have all of the attention activations with some number of them which are going to be the same as degree of this node. So when you put them through the softmax, they're going to become just a normalized mask effectively. So this is not a problem most of the time. Okay. And this neural network has a little bit better performance, but a lot of them are really comparable. Like on a simple data set like Quora, most of them are achieving the limit of the possible accuracy almost. But when you have the attention masks, you can look, you can diagnose which features, which activations were more important than the others, or which nodes. This attention mask is going to be like weights for edges, and you can visualize them and see that some of the nodes affecting the outcome, of the neural network, well, not outcome, but final layer, affecting it much more than the other ones. So you're also going to have some idea of, in your graph, how those nodes connected to each other. How many PhDs does it take to run a notebook? I guess 3. Yeah. Any more questions at this point? No? 4, it takes 4. Yeah. Yeah, just like, no, the attention mask just provides the like amplitude, right? But it also has a weight for the propagating activation in more nuanced way. In more nuanced way. So you have your weights that are going to be propagating activation from one node to another across the graph. But it's going to be like modulated by the attention. So like it's just another layer. Well, not neural network layer, but it's just another computation on top of that. So it can be negative, positive. It's going to be determined by the weights. But the attention is just attention. Yeah. So is it working?
Yeah.
Great. It was working until you started typing, running them. Okay. So yeah, the affix is a little bit easier. We just need to add this line, or
no, we need to change this line. We need to change here.
Okay, we're gonna just re-upload, you know, the correct version later.
We'll re-upload everything later as fixes, but for now, the one notebook Sasha is running, you just...
Yeah, GCN. So this is the gist, I guess, of the most important things about graph neural networks, I would say. They have a lot of theoretical properties, like the spectrums of the graph can be different, and when you're computing the activations, you can see that it affects, like, if you spectral properties of your graphs are better, your neural network is going to work better as well, because it means that the connectedness, the information can be propagated effectively. Most of the time, it does not affect the outcome that much. But the people writing a lot of papers about that, about theoretical properties. Other interesting areas where the graph neural networks can help are actually in chemical, in design of like molecules, complicated like medicines, and finding some molecules with properties, so with some certain properties. In those areas, graph neural networks are also helpful, because when you use graphs, graph is almost the most general form like of data that you can find. You can think of like NLP is just chains of words, right? So this is like the most simple graph that is sequence. If you have images is just pixels in a grid, and we can reparameterize the grid to be a graph. Like one of the notebooks, for example, this GCN, does exactly that. We can use graph neural networks to compute the, like this. So think of it that way. MNIST images are just grids of 28 by 28. And we can find a mechanism of how to connect the pixels together, like in a way that is sufficient for a graph neural network to be able to process it. By the way, the adjacency matrix of this graph looks like this. Oops. Not rendering properly. Yeah. So you can see it's really, really sparse. And in most cases, your graph's going to be really sparse. So yeah, this notebook uses GCN neural network to classify MNIST digits. And in this different situation, the difference is that when you compute several layers of graph neural network, of activations, then you take all of the activations, pull them together, and perform softmax, compute softmax for just binary outcome. Oh, not binary, but number of classes in MNIST, like for 10 digits. So you can do that as well. So you can effectively like classify graphs into categories. And it works actually pretty well. But MNIST is a really simple data set, right? I'm thinking just two-layer perceptron also does pretty well in MNIST. Yeah. So can I help like with any technical details? Like, so if any, does any of you try to run it at this moment? Some of you maybe succeeded even. The first GCN for Quora, maybe with MNIST GCN. Like this one with pretty pictures. Yeah. Does it work? Yeah. So yeah, these are pretty simple. The more complicated they get, the graph neural networks, usually the less effective they are, because each computation, each layer effectively information from radius 1, right? So when you have like 4 layers, it means that information between nodes travels for like a distance of 4. And it depends on diameter of your graph. But most of the graphs don't have like really large diameters. Well, maybe like in NLP, for example, like if you have a chain, like a sentence with 30 words, and you represent like each word with a node, and they're gonna be like connected to a chain, then the diameter of the graph gonna be large. And it doesn't make sense to, so the graph neural networks is almost like the most general form of neural networks because it encapsulates, like the graph data can represent almost any other modality. So this is like why people are interested in them. But the redundancy in data helps design architectures better. So I wouldn't assume that graph neural network would work well on all of the tasks. Like it can work with NIST, but I don't think it's going to beat the ImageNet. Well, maybe you have a sufficient number of layers. Because like the convolutional, convolutional neural network for images, you can think of it as when it performs convolution, just pulls the information from the nearest pixels. So as the same way as GCN does. Well, it has convolutional in the name. So yeah, contrary to what we've been showing to you, it's better to use like specific frameworks for graph neural networks because it's going to be much easier, and I doubt that you can re-implement a lot of the algorithms that needed for that by yourself effectively. So one of those frameworks is PyTorch geometric, as I mentioned. Yeah, and it can work well with other things in PyTorch. So that's why it's also powerful. And it has a mechanism. PyTorch geometric also can work with meshes, and you're going to learn more about that Wednesday on the continuation of this tutorials. Maybe not using this framework, but something different. So I think we're starting to run out of time. So let's just do another round of questions if you have some. It was, sorry for the technical problems, but I think like I just try to provide the most important, details about the network. Yeah. It's a good idea to have like a test object that you like generated yourself, maybe like a graph of like nearest neighbors. Maybe you have something like a square grid and you connect them in a certain way. Just providing the most simplest graphs or like graphs with a known structure. So you can use them as tests, you know, like the absolutely connected graph where you have like maybe like 100 nodes and all of them connected to all of them, or maybe like specific like structures where you have like a degree, each node has like degree of 4. And maybe they have the same features, so when you perform like computation, it can be predictable, so you can debug it that way. And if you like creating this synthetic data set, like classifying the fully connected graphs and maybe like sparsely connected graphs into different categories, just creating the test samples and overfitting on them. If it can overfit, you know, it's like Andrei Karpathy talked about how to test neural networks. And like first thing, you need to overfit on one batch of really predictable samples. That way you can know that if it can overfit on a batch, you can start then training on the full data. But if you're gonna start just writing the train loop and putting all of the data in there, it can take a long time. For example, if you're running this GCN core GCN. In CPU mode, it takes some time actually to compute it, because like the operation of sparse multiplication, sparse dense multiplication, it takes some time to reallocate the memory, to move the things on GPU. So it can be tricky. It's not as fast as just like multiplying matrix by matrix. Because under the hood, what it does is just iterates over the indices of not null elements of the adjacency matrix, or well, matrix that you multiply in. So yeah, it's computationally maybe not as efficient, but yeah. Now, the modern GPU frameworks, they all work with GPU. Yeah, so I'm thinking that's it, right? Thank you for listening.